Good morning, everyone. My name is Felienne. I'm associate professor at Leiden University in the Netherlands. I'm also on Twitter. My Twitter handle is my first name, very easy. So if you want to tweet about this talk, also mention me so I can see what was going on in the room after this talk. The talk that's on the program is this one, Explicit Direct Instruction in Programming Education. But as Martin already said in the morning, I'm not going to give that talk. So this talk has already ended before it has begun. If you were... Thank you, that was easy. Time for lunch. If you really want to see this talk about direct instruction, it is actually on my website. So if you're like, oh, I was super looking forward to that, you can just go and sit in the back somewhere with your earphones and have a look at this talk. If you want to see my new talk that I was just developing maybe this morning, then absolutely stay, and I hope you're in for a good treat to a new talk. Let's start with some audience participation. Who knows who said this? Everyone should learn programming. Who said this? Bill Gates. Any other guesses? Copernicus. Nice. That's not correct, I think. So it's Bill Gates was sort of correct because I think it's every programmer ever. We all love programming. Like, oh, I love programming, and that means everyone should learn programming because I like programming so much. But actually, that leads to a sort of interesting question. If we want to teach children programming, and I know many people that are programmers actually teach their children programming, or they run a code club on Saturdays, how actually do you teach programming? And this is a question I started to think about when I actually started to teach children. About 6 years ago, through the network I know, I ran into some children in a community center in Rotterdam, where I lived then, and they needed a programming teacher for their Saturday club. So I was like, okay, cool. I can do programming, so clearly that means I can also teach programming to young children. I am super qualified. Even though I don't know anything about teaching, I will be fine because I know programming. So what happened, something interesting happened because I started to remember how I learned programming when I was a young kid. So this is me when I was about 10 years old. We had a computer in the home, and I wanted to learn programming. But this is a long time ago, of course. When I was 10, there was no internet. So there was internet, but not in my house. There was no YouTube. There was no Google. So the only thing I had was this book, Basic Computer Games. And it wasn't really a book. I mean, there was not a lot of story in it. For people that also knew these books, they just had printed out basic programs in them. So it wasn't like, hello child, welcome to programming, this is how you do it. It's just, this is a computer game. Have fun. So I just copied everything in my computer, and then of course it didn't compile because I made many typing mistakes, and then I fixed all of those, and then still it didn't run because I didn't understand what I was doing. But after a while I got stuff to run, and this is how I learned programming. And this is interesting because notice the absence of an adult in this story. No one was really teaching me programming. It was very much teaching me programming. And that's an experience that most people of my generation that know programming actually have. Many, let's say the children of the 80s, when they were learning programming, there was no one to teach them programming, and there was no internet, so this is what we more or less relied on. And you can see that in our community as well. Recently, Stack Overflow did a survey among 90,000 developers, and you can see that 85% of people that filled out the survey learned programming before the age of 19. So that means more or less before they went to university, and probably a large proportion of that group of people were, to a certain extent, self-taught. So our whole community is very much, oh, let children explore. Just give them some basic listings, or nowadays it would be Scratch programs, and they just copy it, and they will figure it out. Recently, I did a survey of my own with one of my colleagues, how is programming taught at code clubs, where we actually interviewed people that run code clubs outside of schools, and we found that 71% of code clubs have children explore programming by themselves. So it's really the way to do it, apparently, at this point, is very much mimicking what we did when we were kids. And that was very much what I did when I started to teach those children on Saturdays. I was like, okay, I will buy some books in the bookshop, give them to the kids, and they will learn programming. And that whole exploratory vibe of learning programming is also very, very visible in books you can buy for children today. So I have a few snippets from books that you can buy for coding for children. The snippets will be in Dutch, but I have English translation underneath them so you can see what's going on. So what do we tell children that want to learn programming? For example, the best part of programming is making mistakes, finding mistakes. That says something about who we are as a community, right? It doesn't say the best part of programming is making something that you really want to have, like a game or a website. Or the best part of programming is, you can work for Google and make 100,000 euros a year. Maybe that's what you think the best part of programming is. But no, 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 no. The best part of programming is finding mistakes. I hate finding mistakes. I sort of like solving mistakes, but I hate finding mistakes. I'm like, what idiot made this? Oh, it was me. I don't like finding mistakes. Here's another one. Programmers only learn from making mistakes. And it's sort of ambiguous whether this means if there's a mistake, the only thing you can do is learn from it, or whether it means the only way we can learn anything is by making mistakes, and both are questionable. Here's another one. Again, these are books aimed at children. You will fail often, and it will be frustrating. I mean, they're not lying. We know it's true. If you start programming, you will fail and it will be frustrating. But this is life, right? It's sort of a weird way to market our profession to children. Imagine young Sally being in the bookshop. It's like, oh, I want a new hobby. What shall I do? Maybe horseback riding. Oh, this book, it has pictures of horses. Oh, they're eating carrots. Oh, this looks nice. And the book says, you can totally learn horseback riding. It's fun and it will be hard, but you can do it. Maybe I'll do programming. You will fail often and it will be frustrating. Like, beep, beep, never mind. I'll do something else. It's really a weird thing to say to children, even though, of course, it's true, but learning anything is hard. Here's another one. Never be afraid to mess around and experiment, and in the same snippet, break the rules. So this is sort of true. I mean, playing with code and trying out different things is sort of fun. However, this book is about the programming language Python. Who knows Python in the audience? Okay, a bunch. So for people that don't know Python, this is Python. And Python is very strict about many things. For example, a colon should go there, square brackets should go there. He is messing around and experimenting. Yeah, he's breaking the rules. So Python is very strict. Colons, even if you put a space in the wrong place in Python, Python will break. So it's like, break the rules, but also here's Python, where you shouldn't break rules. So these advices really are at different levels. So at the syntax level, you have to be very precise, but maybe for bigger programs, you break the rules. It's very confusing. And then the final one, from the same snippet you already saw, most importantly, it's fun. Again, not most importantly, this is self-fulfillment and you can build whatever you want, or maybe you can get a good career out of this. No, you should have fun. So to summarize, it's hard, it's frustrating, break the rules, but also put spaces in the right place, and if you're not having fun, you're doing it wrong. Welcome to programming, children. Super encouraging. So you can very much see that exploratory nature in everything we tell children. This is what we believe. You'll figure it out. The compiler is the best teacher. And this is very much how I was also teaching. So I was feeling very good about myself, going to the community center, saying, hello, children, here's programming, figure it out. I'll be in the back having a coffee, feeling really good about my community service to the world. And as I said, in this survey, we found out that this is how many people run their code clubs. Unsurprisingly, the kids were struggling. And I was like, why are you struggling? It worked for me when I was 10. Why do you think this is so difficult? I explained this to you last week. How have you forgotten this 7 days later? It is a miracle to me. Remember, I didn't know anything about teaching, even though my job is being a teacher. I teach in a university. So how is it possible that I don't know anything about teaching? Well, we have an interesting system in the Netherlands, and this is the situation in most countries, that if you want to teach in elementary school, you have to go to school for 4 years to learn how to teach. If you want to teach in high school, bigger-sized children, you have to go to school for 5 years, because you really have to know how to teach. Whereas if you want to teach in a university, you just get a PhD in any topic, software engineering, astrophysics, medicine, doesn't matter. And they're like, oh, you have a PhD. You are very smart. You must understand everything, including how to teach children. So that was me. Technically, I had a teaching qualification at a university level, but it wasn't really compared to what people know if they're teaching in elementary school or in high school. So I got really, really frustrated. I was like, I don't know anything about teaching. How do people learn things? And it was very interesting because those 8-year-olds in the community center on Saturdays really motivated me to learn about learning in a way that the undergrads in the university never did. Because an 8-year-old that's not having fun and that's not learning will tell you. They will take your stupid scratch book, dump it on the table, and say, I'm never coming back to your stupid club, I hate this. Which is hurtful. I was not very happy. I was like, no, don't go, I'm really trying. But it was very instructional for me, whereas undergrads, 18-year-olds, if they're in university and they don't understand something, they think it's about them, even though some of us aren't great teachers. So they'll just go home and cry in their dorm, but they will not tell you to your face. So far, this has not happened to me. 18-year-olds coming up to me and saying, I hate this course, I'm never coming back to your stupid university. Hasn't happened. So 8-year-olds were, for me, very motivating to learn about learning because clearly they were struggling and they were coming mostly out of their own free will and their own free Saturday afternoon to learn. So if you cannot even get people that really want to learn, clearly you're not doing a great job. So I really wanted to understand, how do people learn? So one of the things I really started studying was cognitive psychology, because people have thought about learning and thinking for a very, very long time. And I'm going to take you through, in this talk today, through some of the things I learned that helped me understand learning, but also thinking. So the first thing I studied was a theory by Jean Piaget. Piaget is one of the most influential psychologists of the previous century. And the theory that he has designed, Pietism, has 4 different stages of learning. So what Piaget says is there are 4 levels in which children can behave. If children are really small, between the ages of 0 and 2, then they are at the sensorimotor stage. And that means they know nothing, basically. Babies have no hypothesis. They're just, oh, I'm grabbing things, I'm feeling things. That's why it's called sensorimotor stage. Then as children get older, between 2 and 7, they're at the pre-operational stage. And that means they're starting to form hypotheses about the world. These hypotheses might not be very strong, like, oh, it is raining, the clouds must be sad. It's not a really good hypothesis, but they're trying to make sense of cause and effect, of reasons and actions that are happening in the world. If children age, if they're between 7 and 11, then they can start to really do logical thinking, however, only concrete logical thinking. And that means that they can reason about things that are right in front of them. So they can think, oh, if I will drop this glass, it will fall to the floor. That's something that they can already reason about. But it's harder for them to reason at the abstract level, saying something like, anything I will drop ever will always fall to the ground. That only happens in the formal operational stage after the ages of 11. So there are distinct phases that children go through if they are learning. And this is already very helpful. This is an overview of the phases. But it gets even more helpful if you understand, and there was a second psychologist that followed up on this work, Andreas Demetriou. He says, those stages absolutely exist in young children. However, if you learn a new thing, you will fall back to the lowest level. So even if you're an adult, and if you're proficient in many other things, if you learn something new, then the only thing you can do is act like a baby and grab things and feel things. Who in the audience speaks Greek? Okay, this is not for you. For all the people that don't speak Greek, let me help you feeling a little bit sensorimotory. If I give you a sentence in a language you do not understand, like Greek, and I ask you, do you agree with this? you can't really do it. And here you see that you operate at this lower level because you can read. You can think about agreeing with things. But because this is not in a language you know, you start to grab on to things, almost literally. If you would have this on a sheet of paper, you would probably point with your finger to things you know. You'd be like, oh, I see pi. Probably people know pi because it's well known. Or you see a lambda. People in our programming community might think, oh, that's a thing I know. But you're unable to see the bigger picture. And of course, in a similar way, this can happen if you see a programming language that you've never seen. This is F#. Okay, you've seen that an hour ago, but imagine you've never seen this. You will probably also hold on to things that might be wrong. And here in the top, you see merge heaps and then the empty list H. And you see an equal sign and another H. You'll think, oh, that is assignment. I know it's an equal sign, it must be assignment, even though in this case it is weird because on the left-hand side there's not a variable like you would have in another programming language. There's something like an operation, but still you will be tempted to grab onto this thing you know and say, oh, this is a variable, it's assignment, even though there's evidence of the contrary because you're not ready to see the bigger picture. And that, of course, poses an interesting question. If we know everyone learning something new starts at this lowest level of understanding, how do you get people up? How do you make sure that the children in your community center, or maybe the junior in your team, also moves up to higher levels? And it was this guy, Herbert Simon. You might know him because he won a Nobel Prize in economics, entirely different fields. He actually studied how people solve problems. And this was in the 60s of the previous century. So he wanted to understand how people solve problems, and one of the things that he studied was tic-tac-toe, this game where you have crosses and circles and you have to get 3 in a row. And the innovative thing he did is rather than studying how people solve problems, because it's pretty hard to put people, for example, in a brain scanner and really see what they're thinking, he said, well, what I'm going to do is I'll write an algorithm, and then I can compare the best algorithms to the worst algorithms, and in that way I can try to study how people solve problems by understanding how computers solve problems. So he said, well, what is solving a problem? You have a half-completed solution like we have in the top. And what could you do? Well, you could place a cross in the middle and you would get in that situation. He said solving a problem, the essence of solving a problem is traversing a search space. So there are different options. And if you have to solve the problem, you are going to look at all or some of the options. That's the essence of solving a problem. And that search space can get pretty big, even for a game that is small, like tic-tac-toe. After this first step, you have different steps, because then an O can go in the left, or an O can go in the middle. So a search space of even a small program can get really big. And then some are better and some are worse, because in the first situation, no one wins, and in the second situation, the crosses will win. So what happens if people are traversing this entire search space from this problem? If you have a novice, they're not really good at traversing this search space. So they just try a few options. For example, a novice that has never played this game before might traverse those 3 options. And what Herbert Simon thought is, well, if someone is an expert, they will just try out more things. They have better brains. They process stuff quicker, so they'll just try more things. But that was not the case. It wasn't the case that experts tried more things. It was that experts tried better things. So in this situation, if the expert is trying to figure out how the crosses win, he would or she would look at these tracks. And those are clearly the best ones, because this middle one is a very viable step, because there are 2 ways in which the crosses can win. So solving a problem isn't necessarily about having a better brain, trying more options. It's about quickly understanding, this is viable. I'm going to search in that corner. So if you want people to move up through the levels of Piaget, then it's very much about making people see the right strategies. So they know, oh, this is viable, even without entirely calculating everything. Just getting this intuition for this is where I want to go. So in comes a Dutch mathematician called Adriaan de Groot. This is in the 30s of the previous century, so before Herbert Simon. And he was doing a PhD in mathematics. He was supposed to work on something else, but he was also an avid chess player. So he secretly started to do some research into chess because he was very interested, because he was a good chess player, Adriaan de Groot, but he wasn't an amazing chess player. And he wanted to know, why are other people smarter than I am? Why are they better at chess? I want to understand this, because if I would know why they are smarter, then I could accept it better. So this is what motivated him into really understanding chess. So what he did is he put a chessboard in the middle of a table, and then he had experts and novices reproduce this chess setup. So it was like this. Here's a chess setup. I have an expert and a novice. Look at the board for a little bit, 5 seconds, 10 seconds, 30 seconds. And then I take everything away. And I ask both the experts and the novices to reproduce the chess setup. Who do you think would do better? Who thinks novices do better? Who thinks clearly experts will do better? Okay, most people. Most people are right. Experts do way better. It is relatively easy for experts to just reproduce a chess setup. So then he thought, okay, so clearly the conclusion is expert chess players just have excellent memory. They just really know how to memorize stuff really well. But then he did a second experiment. And in the second experiment, rather than real chess setups, he assigns the pieces randomly. And then he did the same experiment, show this to an expert and a novice for a little bit, a few seconds, and then take it away. So who thinks in this situation experts were still doing better? Who thinks novices were doing better in this situation? Well, both are wrong, because everyone was shit at this solution. No one knows how to remember anything if it's a random setup. Interesting, by the way, Adriaan de Groot wrote this up in his PhD thesis, that if you want to, you can still easily find on the internet. And the idea that he had in his PhD thesis was chunking. So he said, what happens in people's brains is an expert, rather than understanding or remembering, oh, there's a rook at a5 and there's a pawn at b7, they will just say, oh, this is Sicilian opening, but that one rook is in a different place. So rather than understanding or remembering individual pieces, they would just remember a big setup. And the interesting thing about his thesis is Herbert Simon, that you remember from problem solving, learned Dutch to be able to read Adriaan de Groot's PhD thesis. So it was very, very influential, and later helped that research into problem solving, because at that point in time, not a lot of people were working on this. So it was very, very influential thesis, and people even learned Dutch to be able to understand this. So if it's not superior memory, if it's not the experts just can remember everything better, what makes experts? And that is actually where that chunking comes in. Because our short-term memory of people is very, very, very limited. People used to think that the short-term memory of people can only hold between 5 and 9 items, 7 plus or minus 2. This is, again, old research from the 50s. Newer research actually suggests that it might be 4 plus or minus 2. So our short-term memory can only hold between 2 and 6 items. It's really a mystery that I can stand here and also speak and also flap my arms and legs with such limited brain capacity. How is this possible? So let's do another experiment in which you can participate. I am willing to bet 1,000 euros, what is it, 4,000 zloty. I will show you a sentence, just very briefly, like Adriaan de Groot did with the chess setups. If you can reproduce the sentence, I will give you 1,000 euros. Are you ready for this challenge? Any takers? Okay, here's another one. This one is slightly easier. I'm willing to bet like 400 zloty for this one. Oh, and do not take pictures. No cheating. Are you ready? So that was easier, but still pretty hard. Now I have a third one for you. I'm not betting any zlotys on this one because it will be really easy. But notice how all the sentences I've showed you are the same length. So here's another one. So why is that so easy? They are the same length and they have the same number of characters. This is exactly what chunking is. Because now in your brain, you're not thinking, oh, this is a half round, and that's a round with a squiggly, and that's like a cross and a long stripe. You can immediately chunk this into 3 things. Cat loves cake. And that easily fits your working memory. There's even room left in your brain. You can think, oh, cat, oh, I have a cat. I miss my cat. It is so cute. Or you can think, oh, cake. Maybe they'll have cake in the lunch break. Cake. While also remembering these things. So there's room in your brain. And this is exactly what chunks are. So this is what the expert chess players were relying on. Oh, one thing. And then it would easily fit your working memory. If you say, oh, it's Sicilian plus a rook, rather than, oh, a rook and a pawn and another pawn. It's too much. So then the question becomes, if you want to understand again how to move people up to the highest level of understanding, it's not necessarily how to make people see the best strategies, rather it's about how to make people remember the right strategies. Because how can you chunk those words so quickly? Because you know all the letters, you've memorized all the letters. And because you know what a cat is and you know what a cake is. Only because you have lots of things in your long-term memory, you can easily chunk things. Again, same with the chess players, because Sicilian opening is in their long-term memory. They can quickly retrieve it when they need it. And for that, we need to know another concept, the concept of cognitive load. If you are actually wanting to win the 4,000 zloty and you want to remember this sentence, if you try it, your brain gets really full. You can almost physically feel it. You'll be like, oh, a circle with a dot and a sigma reverse and a stripe and another big C. You'll feel something that's called cognitive load. Your brain gets really, really full trying. And this theory, cognitive load theory, is created by an Australian researcher called John Sweller. This is a bit more recent, in the 80s of the previous century. So what Sweller said is there are 3 types of things you can do with your brain if you're solving a problem. The first thing is intrinsic cognitive load. So if you're solving a problem like this one, you have an A and a B and a C on a triangle, and you have to figure out what the C is. And you get A is 8 and B is 6. This is just difficult. This is intrinsic load. Problems are difficult. And then, of course, if you know from your long-term memory that you have to use the Pythagorean formula, it gets slightly easier, but it's still a hard problem because you have to do some calculation. There's a second type of load, and that's extraneous load. And extraneous load is unnecessary complexity. For example, if you have this problem, the same problem, rather than presenting it like this, you could also present it like this. This is not really making the problem harder, but it is giving your brain extra things to do, because rather than having 8 at the right place, you have to go to the table and say, oh, 8, oh, A is 8, oh, B is 6. And then sometimes there's extra fluff that doesn't really matter, like consider these values for A and B. Yeah, I knew that, it had an equal sign. So that is all filling your brain with not necessarily things that are contributing to thinking. And then there's a third type of cognitive load, and that's called germane load. And germane load is good load. Germane load is what you can use to store things in long-term memory. So if you've 10 times seen a cat, you're like, oh, this is a cat. Now I know what a cat is. Next time if I see one, I can, from my long-term memory, retrieve how you spell the word, for example. So that is what makes your brain remember things. And Sweller did some experiments in which he really wanted to try to understand how to teach, and this was about mathematics, to children understanding cognitive load. So he has this paper, it's called The Use of Worked Examples for Problem Solving, and he had 2 groups of kids. One group of kids got, let's say, a traditional algebra problem. So A is 7 minus 4A, solve this for A. It's more or less what you would get in math class. What the other group got was a recipe. So they just got, oh, if you have something that is of the shape A is B minus CA, what you could do is move the CA to the other side of the equal sign, but then it has to be a minus, and so on and so forth. And then they got to solve the same algebra equations as the first group. Unsurprisingly, of course, the second group did way better, because, well, he gave them the recipe how to do it. So clearly they were doing better. But they were doing spectacularly better. So they were solving the problems in 1/5 of the time of the first group. So 20% of the time, pretty spectacular. But also, and here's the kicker, they also did better on different new problems. And that is interesting. And this is what we often say, no, you shouldn't tell children how to do it because then they only know how to do this one problem. That is not true. Because what probably happened is this group that got the recipes had some germane load in their brain left. So they had room to store the strategies. And a strategy like, oh, if you move something to the other side of the equal sign, you can always do that, but then it will be minus. That's always useful. And a strategy like, oh, you can divide both sides of the equal sign by the same thing, that's always useful. So this other group probably, they could solve the puzzles, but they didn't have room in their brain left to store anything. So the easier sometimes you make problems, the better people can do new problems. So in summary, what we've learned so far about the cognitive architecture of the human brain is there are different levels of learning, and even you're an adult expert, if you learn something entirely new, you'll be a baby again. What's very important and what will help you not be a baby is chunking. If you remember big chunks of things, so you can get them from your long-term memory. And a third thing we learned is cognitive load. If your brain is very full, you cannot really remember or process new things. So maybe you're like, why is this interesting? I don't care about the cognitive architecture of the brain. I care about programming. Well, why I think this is very interesting is because I hope it will give you a new vocabulary coming into work Monday. I hope that you start thinking in this way about your teammates and maybe also about yourself. Because if you have maybe new teammates and they're really struggling, they're like, oh, I have never seen Java before, help, I don't understand anything. Rather than thinking, oh, he knows nothing, he is such a useless junior, maybe you can think, oh, he's acting in a sensorimotoric way. He's a Python programmer and he's never seen Java, so of course, everything about OO in Java will confuse him coming from Python. So clearly he will grab onto things that do not make sense in the Java context. So I think this is a valuable thing to help. In a similar sense, maybe you have another teammate and you're like, oh, this teammate from another team that I don't work with a lot, they know nothing. Every time I speak to them on the phone, they sound so clueless. Rather than saying they know nothing, maybe you can say, oh, they lack enough chunks. They've never seen C# so often, so they don't know by heart how to produce a for loop, for example, in C#. So they just do not have enough chunks. Maybe I can bring them some chunks. Maybe I can help them build up a bigger vocabulary of C# chunks. And I also hope, and this has certainly worked for me, that it will also help you to reflect on your own thinking. Because sometimes I'm learning a new programming language. For example, Elm, I did a bit of Elm at a workshop a while ago. And I'm like, oh, I'm too old to learn. I have already learned 10 programming languages. Clearly, I will never ever learn another one because my brain is just, aging. And I'm like, no, I do not know nothing. My cognitive load is just too high. I'm just a healthy, functioning human with only 2 to 6 working memory items. This is normal. You are fine, Felienne. You can learn Elm. You just need a little bit more chunk and lower cognitive load. So that definitely, for me, has been very, very relevant. Understanding this vocabulary to help me understand learning of people around me and learning of me. So I certainly hope that it will do that for you as well. Help you to understand, yes, it's normal. They are not stupid. They are fine. They just need a little bit of help. And this has also really helped me coming back to teaching the children to really understand how to teach programming. Because once you know about the cognitive architecture of the brain, you can teach, you can learn, but also you can teach in a more effective way. For example, a revolutionary idea that I've implemented now in my teaching is I tell students how to solve problems. It is a surprise, right? It's very weird because we as a field, we're not used to telling students or children to solve problems. We are used to giving them problems and saying, oh, keep going. Oh, do you have a mistake? Do you know what a mistake is? It's an opportunity for learning. The compiler will help you. I'll take another sip of coffee. But people have actually studied this. There's a very old paper from the 90s that's called The Case for Case Studies in Pascal. And I read this paper, and knowing what I know now about how human minds work, I was like, oh, this makes so much sense. So what did this paper do? Quite revolutionary in the 90s. They had 3 groups of high school students. The first group, traditional setup, they said, here, solve this problem. Once they had solved the problem, they got to read experts' code. So like the teacher also solved the problem, like, here's how I did it. Very traditional setup. Solve it first, and then I will show you how I solved it. The second group, almost the same, but rather than only getting the code of the expert, they also got an explanation. So, oh, here I use a variable, and here I use a for loop because reasons. The third group did not write any code. The only thing they got is the code of an expert plus the explanation. So this first group, the first group, write and read code was what the teachers really preferred. So the teacher said, no, the student, they should code. You cannot just give them the solutions. That is madness. However, the second and the third group did best. They did equally well. So it doesn't even matter if you write your own code or you do not write your own code, as long as we just give you the code of an expert plus an explanation to read, you'll do fine. So this was really a course of a few weeks in which the third group did not program at all. And yet they performed as well as a group that did program, and better than a group that only programmed and did not get any explanation or feedback. If you know about cognitive load, this makes all the sense in the world, because that first group, they were only focusing on the problem. So of course they couldn't remember anything because they had no room. Whereas those 2 groups, and especially the last group, had lots of cognitive room because they were not programming. They were not like, oh, here's the compiler, you forgot a semicolon. Pff, oh, my brain is empty. I forgot entirely, who am I, what am I doing here? No, they could just read the code and learn and store strategies in their long-term memory. So explaining explicit strategies, it works really well. And another thing, this is my own research that we have been exploring, is helping children to read code aloud, to vocalize syntax. So for you to understand the effect of this, let's do one more mandatory audience participation moment before lunch. We're going to do an experiment, because also on Saturdays, I'm a scientist, so I science all the time. So what we're going to do is, this is you. I will give you a sentence. You read the sentence in silence, in your head, and once you reach the end of the sentence, you raise your hand. Very well, very well. There's one caveat though. I will show the sentence in 2 steps. So it'll be like this. There is a cat. Read it in silence, in a tree. And then when you reach the end, you raise your hand. Yes? Are you ready? Okay, one more. Yeah. So I wasn't counting, but statistically, the second one should take you longer. Because you read, I have a tear. And then when the second part appears, you're like, oh, it's not a tear, it's there. English, it's the worst. So you have to go back, repronounce the sentence in your brain, and then read it again. So it takes you slower, because how something sounds in your brain, this is called subvocalization, really, really matters. It's like, ugh, this is so confusing. But if we're programming, if we're teaching programming to kids, we don't sound stuff out in our brains. We just read it in silence. So we actually asked a bunch of kids. I asked high schoolers. I said, what is this? They're like, oh, I know this one. X is 5. X equals 5. X gets 5. Set x to 5. Assign 5 to x. These all make sense, but probably this is inducing cognitive load on the brain of high schoolers, because they're reading the code and they don't really know how to do it. They haven't automated this like they've automated English or Dutch or Polish. So we should actually tell this to children. We did an experiment in which we had high schoolers repeat source code aloud. So we're like, Repeat after me. X is 5. 4i in range. Open bracket 4, closing bracket colon. Very much like the tables of multiplication are also taught in schools. Unsurprisingly, not very surprising, this really worked. The group that read code aloud every week did way better on the syntax test. It makes all the sense in the world because they had germane load. They had entirely automated the entire process of reading Python, so it took them no energy, just like it took you no energy to read Cat Loves Cake. You need that sounding out to be able to listen to code in your brain. And this is a paper we just published in May of this year. And this is an interesting paper because here you see the culture clash. Because people in programming, if I present this to them, maybe people will be angry after this talk as well. Sometimes people are angry. They're like, no, source code isn't meant to be read aloud. That's not what programming is for. Programming is for the compiler. This is not for humans. This is so weird. It feels so weird to me reading Python aloud. We're not used to that. So programming is mildly upset. But you know who's more upset? Elementary school teachers. I go to, this type of things, but then with school teachers. And I give this talk, and they're like, okay, Dr. Hermans, so it's 2019. And you people in programming have figured out that making children read stuff aloud improves their memory. Tell me more. We didn't know this. We never do this in elementary school. We do not read anything aloud. Not language, not the tables of multiplication. We never do this. What a wonderful finding. Slow clap. We are so impressed. They're like, yeah, duh, did you really need to run a test for that? So this is really these two cultures of, in programming we think, oh, people will just magically acquire this knowledge. And in education, they're like, yeah, of course you explain stuff to people. What do you think a school is for, really? So that is interesting. Vocalizing syntax, helping children automate stuff they learn is really, really helpful. The end. So before we really go to the end, let me summarize my entire talk in like 1 or 2 minutes because I know it's almost lunchtime, so maybe you're low on energy and I tend to speak rather quickly. So let's give you an opportunity to get the gist of the entire talk in a bunch of slides. So I got really interesting from teaching children programming. How do people learn things? It got me really motivated to deeply understand this. And the interesting thing is, people's short-term memory is really, really very small. It might hold only 2 to 6 items. So you need something to make your brain better. Something to actually make your brain work better is called chunking. If you have lots of interesting things, like letters or the sound of Python commands in your long-term memory, you can use that to solve problems. That's because cognitive load, if your brain gets too full, if you overload the limits, the small limits of short-term memory, you will not learn anything, and the green part will be not there, and you will not remember. This has extensively been demonstrated in language education, but also more related to programming, maybe in math education. We know if we just tell children, this is how you solve a problem, and then they practice a lot, they will do better. We know that that helps because we understand how brains work, but in programming, we're still sort of figuring that out. For example, we know this very old study from the 90s, understanding the brain helps us understand that study. Yeah, of course, if you just have children read code or students read code, yes, they will do better because you just tell them what to do, they memorize it, and they can reproduce it later. And this has inspired my own work on how code sounds, because that's another thing. We just wanted to automatically go, if a student is exposed to a piece of Python, they should just know, oh, the equal signs, it means x equals 5. That's what it means. It should take them no energy deciding whether that's equals or is or sets, because that is only going to confuse them. The end. If you like listening to me, you might want to also check out my Twitter, check out my website, felienne.com, where you can also download all my papers if you're interested in really reading the statistical details of the setup that we did. I'm also one of the hosts of a radio podcast called SE Radio that's on iTunes and on the internet. So if you would like listening to me, maybe you also want to listen to our podcast. We have shows every other week where we interview leaders in the software engineering field. I don't think we really have time for Q&A, but I will be around all day. So if you want to ask me questions, we can totally do that in the break. I will answer one question, though. People always ask me, have you made those slides yourself? Yes, I have. I'm very proud of that. I make them on my iPad with an app called GoodNote. So I draw everything on my iPad, and then I drop it into Keynote. So yes, I have done those slides. And before we really go over to lunch, I have one thing I want to ask of you, because as I said, I'm a scientist. I'm also sciencing on Saturday. And we're currently running an online survey about how people view different programming languages. Because maybe you gathered from my talk that I'm very interested in how do we see programming, how do people see programming within programming. So what we're doing is we've made this website where you can rank programming languages from least to most programming. So you can say, well, MATLAB is not very programming. PHP is maybe a little bit programming. Assembly language is real worthy programming. By definition, this is sort of vague. We put this on Twitter last week, and then people were like, yeah, but what is least program? What is most program? That's what we want to know, because we know those feelings exist in our community. We know that some people have this idea that maybe some programming language is more valid than another programming language. So you can rank as many as you want. You can add your own programming languages as well, whatever you want. And then we have one question in the survey, apart from what's your age and where you're from. What did you have in mind as you were placing the languages? So there we want to understand, what do you think makes one language more programming than another language? So it would make me and Lara, that's also in this survey, really happy if you would do that. So we made a short link, bit.ly/pl-views, where you can go and fill out your programming languages. So as like a return the favor for me for giving this talk, maybe you want to fill out my survey, maybe you want to share it on Twitter. That would be very nice. The real end. Thank you very much. Enjoy lunch and enjoy the rest of the conference.